We are now going to prove one of the most basic but also very important properties of cyclic groups. Namely, that if you take a cyclic group and you take its subgroup, any subgroup, then the subgroup is also cyclic. So, here's our theorem. Let G be a cyclic group and let H be a subgroup of G. Then H is cyclic. So in other words, any subgroup of a cyclic group is cyclic. So let's prove this. So suppose X is a generator of G. Then any element of H, so any element of G, and hence also any element of H, is a power of X. Among other things, H is a subset of G. So every element of H is an element of G. And I know every element of G is a power of X. So every element of H is a power of X. So if H is just a trivial group, so consists only of the identity, then it is cyclic. Okay? A trivial group is a trivial example of a cyclic group. That is, the identity is a generator. Of course, every element of the group that consists only of the identity is a power of the identity. So then we're done, then it is cyclic. Otherwise, H contains some positive power of X. Well, why is that so? Why can't H only contain negative powers of X and the identity? Well, suppose that X to the minus 5 is in H, but H is a group, so the inverse of that element is also in H. So the inverse of X minus to the minus 5 is X to the 5. So if it contains X's with negative exponents, it must also contain X's with positive exponents. So let n be the smallest positive integer such that X to the n is in H. Okay? If it contains some positive powers of X, as it must, then it contains, one of them is the smallest possible power. So let n be the smallest such power. Now let's take, so what am I trying to show? So we will show that X to the n is a generator of H, i.e. that every element of H is a power of X to the n. Will that do it? Yeah, we're trying to show that H is cyclic, so we're trying to show that it has a generator. If I show that X to the n is that generator, then I'm done. What does it mean to show that X to the n is a generator? That means to show that every element of H is a power of X to the n. So let's do it. So let's take some H that is in H. So let H be in H. Right? So I want to show that this is a power of X to the n. Well, as H is also an element of G, surely, right? Everything in H is an element of G. and X is a generator of G is cyclic, then this is also a power of X. We know H is equal to X to the M for some M in Z. Okay, so now again I'm going to use the divisibility property of Z. So by the divisibility property of Z, we have that I can write M as Q N plus R for some Q R in Z, and R is between 0 and N. All right, then what? Then what about H? Then H is equal to X to the M, which is equal to X to the Qn plus R, which is then equal to X to the N to the power Q times X to the R. And note, X to the N is an element of H. Right? That's how we chose n. N was the smallest positive integer such that X to the N is an element of H. Oh, but if I take H as a group, so if I take any element of H and multiply it X times by itself, that is still an element of H. So that whole thing in the blue box is an element of H. So I get X to the R is equal to this thing inverse times H. Okay? So I multiply, so I'm looking at this, at these two, and I multiply, this is an equality, H is equal to that, and I multiply on the left by the inverse of that. So I get that X to the R on the right hand side, and on the left hand side I get the inverse of that times H. The inverse of that times H. But what do I know? This thing inside, right, that's an element of H. Just as we said here. But H is a group, which means the inverse of an element of H is also an element of H. So that whole thing here is also an element of H. But H is also an element of H. And H again is a group, so if I take an element of H times an element of H, I get an element of H. So that means this whole thing is an element of H, i.e. X to the R is an element of H. So X to the R is in H. Okay, so now let's see what this tells us. If R is positive, right, that's one of the options, that it's positive, then this contradicts the minimality of n. How so? N was the smallest positive integer such that X to that integer is in H. And R now is positive and it's smaller than N. So that would be a contradiction. So R must be 0. i.e., what do we get? If R is 0 in here, that means that N divides M. Okay, so what? Thus, m is equal to nk for some integer k in Z, right? M is a multiple of k. Okay, well, still so what? Before I erase it, h is equal to x to the m. But h is equal to x to the m. And m is equal to nk. So that's x n to the k. So what have I just shown? I have shown that h is a power of x to the n, which is what we wanted. So h is a power of x to the n, as desired. Okay? Remember, we wanted to show that h is a power of x to the n because h was an arbitrary element of big H. And if you can show that it's a power of x to the n, that means x to the n is a generator of big H, which makes big H cyclic. So that's what we just showed.